This is a visual representation of what the area under the curve looks like. It's basically the pink striped area above the x-axis, but under the graph of f of x, from the left limit, which is a, to the right limit, b. We're going to start out with an easy practice problem to get us accustomed to solving areas under a graph. The following equation of the graph is the absolute value of x minus 5. As we can see from the picture, the area under the equation absolute value of x minus 5 are two triangles. The one on the left, which is shaded in blue, can be solved using the equation for the area of a triangle. The triangle on the right, which is shaded in blue and pink, can also be solved this way. Using the equation of the area of a triangle, the left triangle equals 1/2 and the right triangle equals 2. We can add these two values up, which equals to 5/2, and this is basically the area under the equation of the graph absolute value of x minus 5. We can also use Riemann sums to solve for the areas under a curve. Riemann sums involve using rectangles and their heights to solve for the area. Some notations that are useful are as follows. L sub I is the height determined from the left side of the subinterval. R sub I is the height determined from the right side of the subinterval, and M sub I is the height determined from the midpoint of the subinterval. The graphs on the left are representations of these notations. The notations in pink, blue, and green are some other helpful notations. You can pause the video now and take a look at these three notations. But overall, the notation for Riemann sums is basically delta x, which is the base of the rectangle, or the difference between the x values, multiplied by, in parentheses, f of x, which is the height, whether the left-hand approximation, the right-hand approximation, or the midpoint approximation, plus f of x, and so on. We can put it in this format if the delta x or base is the same for all the independent rectangles, or if the subintervals are equal in length. One question that pertains to solving the area under the curve, especially when using Riemann sums, is whether the area is an over or underestimate. If the function is decreasing, left-hand approximations are overestimates and right-hand approximations are underestimates. If the function is increasing, left-hand approximations are underestimates and right-hand approximations are overestimates. Midpoint approximations are still estimates but can be decided as over or underestimates for both decreasing and increasing functions. And these concepts are especially important for word problems. Now we're going to apply Riemann sums to solving the area under a curve. These are some important steps to take. Find out what A is, which is the left boundary, and what B is, which is the right boundary. Delta x, or the base, is b minus a divided by the number of subintervals the problem tells you to have. Find out whether the problem is asking you to find left-hand approximations, right-hand approximations, or midpoint approximations. Also, to solve for f of x, just plug the x value back into the equation of the graph the problem gives you. The example problem says, approximate the area under the curve f of x equals square root of x plus 1 from the interval of -1 to 0 using 4 subintervals, and find left-hand approximations, right-hand approximations, and midpoint approximations. For the left-hand approximation, a is -1 and b is 0. This is the same for right-hand approximations and midpoint approximations. The delta x, or base of the rectangle, is 0.25. Because we are using 4 subintervals, this is the same for right-hand and midpoint approximations as well. But the x values you plug into f of x are different for all these approximations. For the left-hand approximation, we take values starting from the left side of the subinterval. So -1, -0.75, -0.5, and -0.25. For the right-hand approximations, we take values starting from the right side of the subinterval. So -0.75, -0.5, -0.25, and 0. For midpoint approximations, we have to actually calculate what the midpoint is of each of these subintervals. So take the sum of the left side of the subinterval with the right side of the subinterval and divide by 2 to find the midpoint between these 2 points. Now plug all these x values back into the original equation, which is square root of x plus 1, and add all these values up and multiply by 0.25. This problem also utilizes Riemann sums to solve the area under the curve, but is now a tabular-based problem instead of a graph-based problem. Estimate the area under the graph using the chart below. Do this estimation by right endpoints, left endpoints, and midpoints. First off, we can't solve midpoints because the intervals are not equal. We don't know f of x equals 1, and also the intervals are unequal, so we can't set x equals 2 as the midpoint. If the intervals were to be equal as shown in the green graph, then we could use midpoints. The x values for the midpoints would then be 2, which is the midpoint between 0 and 4, and 6, which is the midpoint between 4 and 8. In the table, I listed the delta x values, which we can see are the differences between the x values, and I also listed the left-hand values and the right-hand values. Left-hand values start from the left side of the subinterval, so they are 1, 3, 2, 5, 4, 6, and 7, whereas right-hand values start from the right side of the subinterval, so they are 3, 2, 5, 4, 6, 7, 2. Once we've found these x values, we can multiply each individual value, whether the left-hand value or the right-hand value, with its corresponding delta x value. We can't use one universal delta x value for this problem because the subintervals are unequal. By using Riemann sums, you can find the distance traveled. Distance traveled is the area under the graph of a velocity function. In the example below, the x value is the time in seconds, and the y value, or the f of x values, is the velocity in feet per second. For this particular problem, we can use midpoints because the subintervals are equal. So thus, x equals 5 and x equals 15 are the midpoint values. If we were to solve for the left-hand approximation, it would be 540 feet, the right-hand approximation would be 600 feet, and the midpoint approximation would be 630 feet. This is another example distance problem utilizing Riemann sums. In the table, the x values is the time in minutes, the y value, or the f of x values, is the velocity in miles per hour. We're going to use midpoint approximations for this problem because midpoint approximations tend to be the most exact approximations out of all three approximations. So because the subintervals of this particular problem are equal, we can use midpoint approximations to solve the area under the curve. So x equals 2 will be our midpoint x value, and x equals 6 will be our midpoint x value as well. Because 2 is the midpoint between 0 and 4, and 6 is the midpoint between 4 and 8. So delta x is 4, and we're going to use f of 2 and f of 6. F of 2 is 60 and f of 6 is 50. 60 plus 50 is 110, multiplied by 4 is 440. So thus, 440 miles is the distance traveled. Oil leaked from a tank at a rate of R of t liters per hour. The rate decreased as time passed, and values of the rate at 2-hour time intervals are shown in the table. Find the total amount of oil that leaked out using midpoint approximations. So in the table, the x values is the time in hours, and the R of t values are liters per hour. So by using midpoint values, we can see that x equals 2 equals the midpoint value and x equals 6 equals the midpoint value because 2 is the midpoint from 0 to 4 and 6 is the midpoint from 4 to 8. Thus, the delta x values are 4, and f of 2 and f of 6 will be our heights. F of 2 is 7.6 and f of 6 is 6.2. 7.6 plus 6.2 all multiplied by 4 is 55.2. And this is the total amount of oil that leaked out. These are some common mistakes when solving for the area under a curve using Riemann sums. Using incorrect left hand, right hand, or midpoint x values. So read carefully what the question is asking you to do. Not using function notation. For example, delta x multiplied by, in parentheses, f of x plus f of x plus f of x. First of all, know what function notation is. And second of all, read the question and don't forget to put your answer in function notation. Computational mistakes. For example, solving for the midpoint or plugging x back into the original f of x. Check your work and use a calculator you know how to use on the test. For distance problems, make sure the units are continuous. For example, if time is in seconds, velocity has to be in feet, miles, or meters per second. Read the problem carefully because you may have to change units if these units are not continuous.